It says they determine the support reaction in the joints of the following truss. Okay, support reaction. Where are my support reactions? I've got a support here and a support here. So let us draw the free body diagram of the structure. So I will do this. I will make, I will have a point here. This point A, I'm talking about point A now. Point A can rotate, but it cannot move in XY direction. So I will have a reaction force and I will have a reaction force here. Now let's look at support C. C is a rocker. It can rotate, it can move left, right. I can lift it, but I cannot move it down because there's a ground there. So I will have a reaction force here. And there's an active force being applied here, which is 5. And then, yes, I have to put the dimensions here. So ignore the dimension at the moment. But is this the free body diagram of the structure? Am I right?
Yes, sir. Yes, sir.
So you can clearly see, if I want to find the reaction force, there's no need to do the analysis of the members inside. I'm not doing any analysis on this member, or this member. I'm not doing that. I am doing it on the complete system. I'm looking at the external forces. So, in simple words, in most of the cases, when you do analysis for the support reaction, you look at the external forces acting on the body. You do not go inside the body. Is that clear?
Yes, sir.
Okay, so let us look at the free body diagram of this one, which looks something like this. And you do your analysis and you get all your values out. Okay. Now, same example. Okay, same example. Stay with me. Let me do finish this one and then we'll have a break. Same example. Remember this example, force being applied up here, and I've got two support reactions. Now, same example, it says here, determine the force in each member of the truss and indicate whether the member are in tension or compare. It's exactly the same example, but now it's not saying that to find the reaction forces. It's saying find the force in each member. Okay, each member. So let us have a look at. I need the drawing. Come on, yeah. Okay, so let us remember this point. Where it? Come on, I need the point. Where this? Yes, this one. Always be sure to choose a joint having at most two unknown and at least one known force. Now, in the truss, in the frame, what you need to find is there any joint where you've got one known force and a maximum of two unknown. Having one unknown is very good, but if you've got unknown more than one, then look for the joint where we've got maximum of two unknowns and one known force. So in this case, now because we need to find the force on each member, so where we should start? We should start from point joint A. Well, I've got uh, two unknown reaction force and two unknown member force. If I look at C, I've got two unknown forces from the members and one unknown force from the ground. Okay, can do that. So let us look at point B. At point B, I've got two unknown forces because of the members, but I've got one known force. So this is the criteria. So I will start my analysis from joint B because B has got one known force and two unknown forces. So I will I will draw the free body diagram of joint B. So pin B, let me draw a pin B. This is the pin B, okay? Pin B. On pin B, I've got a force being applied. This is the force applied on pin B, which is 500 Newton. Okay. And I will apply a force downward because of this member, this one. Okay. I can do this also. It's your call. You have to stick with it. So if I do this, it's your call. Okay. So I've got this force. I'll write this member one. So this is because of member one. I've got another member two here. I'll write M2 here. So I've got another member here. I can do this. But if I look at the diagram, I would say that I've got one force acting here, the other force acting here, then and it's in equilibrium. So this one should be in this direction. Or I can do this, that I will have this member upward and then this member downward. Then okay, a bit of it still doesn't make sense because you got this force component here and there's another component here has to be balanced. So I can do this. I can stick with the direction downward here. And my answer will tell me this is the wrong direction because the answer will be negative. But as I said, use common sense. Common sense clearly tells me that one of the force has to be in the upward direction because the component of this will balance this one and the component of this will balance this one. Okay. So this would be my M2. So this is the free body diagram of pin B. Am I right?
Yes, sir.
Okay. So pin B, I've got one known and two unknowns. Okay. So I know this angle here, which is 45. Won't go into the details because you maths, simple maths, and you apply equation of equilibrium. So you've got your BC. You've got your BC, which is 707 Newton, and you've got your BA, which is BA is here. BA. Now, watch. The answer coming out is positive. So it means the direction assumed here is right. Oh, sorry. The direction assumed here is right, and the direction assumed for this one is right. Now, this is a pin is being, if I look at BC, I look at BC, it's upward, so it's in compression. I'll show you when I draw all the members. So forget this at the moment. So let us now. So we now know the force in BC. That's sorry in BC. So we know the force in this member, and we now know the force in this member. Okay, now we need to know the force on this member now. So I can pick a pin A or pin C. If I pick pin A, then I've got three unknown forces, two reaction and one this, but I've got one known force, so not the right choice. If I look at C, I've got one reaction force and one member unknown force, but I've got one known force which I've already calculated. So I will go for joint C. So let us look at joint C. So let me draw the free body diagram of pin C as my pin C. Okay, and I've got force BC upward, so it's the same force in the opposite direction downward, which is 707.1. I've got a reaction force acting from the support, so that's my reaction force R. Now I need to find the force on this member, so that is this member here. I can write AC force. Now, if common sense tells me that I've got this force acting towards the the right, then something has to balance it. So I guess the right direction would be this
Left.
one, I guess, AC. Okay, this is just common sense. Okay, so now this is my free body diagram of pin C. And I can now apply equation of equilibrium, which is exactly same here. I can apply equation of equilibrium, and I will be able to get the value of C. Now, so do I need, what was the question? Just determine the member force. Let me see. Determine the force in each member of the truss and indicate, okay. So I've calculated this one, and this one. I don't need to do analysis on A. Okay. There's no need to do analysis on A, but they've done analysis. There's analysis for A, but don't worry. We've already got the member forces. So forget that. So summary of the result, look at this. That's where I want to spend more time. B. Should we concentrate on B? Yes. Okay, let's go back to B. Look at B. Okay. Look at the B joint. Memorize it. You got force acting in this direction towards the right. You got the force acting downward, and you got the force acting at a certain angle. Okay. So, sorry. Why did I do that? That's my B. So this is my 500 Newton. This is my 500 Newton here also. I'm taking it from there. And I've got another force acting here, which is approximately 707. Okay. So this is what we calculated. Okay. So let me, oh, I can't copy it. Sorry. No, cannot copy this one. So remember this, you got force acting towards right, force acting downward, and you got the angular force acting upward. It is exactly the same as here. Concentrate on this part. You got the force acting towards right, down at an angle. The same point, look at this force. Okay, this force is coming from the member, this one. Okay, coming from this member. So if I look at the member, the same force now applies in the opposite direction. If you look at this force is from the member, same force applied on the member in the opposite direction. So it clearly tells us that this component is under compression, this one is under tension, and this one is also under tension. Is that clear to everyone?
No.
Sir, can you explain this point again?
Okay. I'll go back to the same example. You remember that box one and table? Everyone knows that now. If I draw the free-body diagram of the box has got weight acting downward and it's a reaction force R. If I look at the table, then the table for the table, you've got that reaction force, same reaction force now acting downward. If I look at the table, it's downward. If I look at the box, it's upward. Is that clear?
Yes, sir.
It's exactly the same. When we look at point B, we calculated the force acting on pin B. Where's pin B? Come on. Yeah. We look at the forces acting on pin B. So pin B, we had this 500 Newton coming from here. We had two reaction force from the members, which is given here. Okay. So if I look at the pin, the force is upward. If I look at the if I look at the pin, the force, sorry, I'll pick this one. Okay. If I look at the pin, BA is acting downward. If I look at the member, for the member, the force is acting upward. Come on, the force is acting upward. this force and this force is the same, but in opposite direction. If you're looking at the pin, it is downward. If you're looking at the member, it's upward. Same like the box and table. Is that clear?
Yes, sir.
Okay. Gentlemen, can I continue for another 10, 15 minutes and then we'll end the lecture, or you want to have a break?
No, sir,
We'll
continue.
10 to 15 minutes then.
Continue.
Okay.
Sir, I
Yes.
had a question.
Yes.
Sir, when we say we are resolving the joint, do we like find the forces for the pin or the member?
Pin. If you remember, if you're drawing the feedback diagram for the pin, then you draw only the pin and cut it off from the surrounding. You do not look at the member. If you draw the feedback diagram for the member, you do not look at the pin. Is that clear?
Yes, sir.